Welcome to lesson 4.3.1, and in this lesson we will be solving trigonometric equations. Solve 5 sine theta plus 6 is equal to 3 sine theta plus 5, where theta is between negative pi and 2 pi.
So this first question that we're going to solve here, this equation, it's not as complicated as some of the other ones are going to be here because it's more of a linear function. Okay, the functions with the variable in it, there's no square, there's no cube. It's just sine of theta here. Now, when we start these equations here, the first thing I want you to look at here is the domain over which the answer, in which the answer is going to be that we're looking for here. Okay, so let's just take a quick look at what this is saying here. So here's my coordinate plane. My domain is from negative pi out to 2 pi. So negative pi, and remember, we're typically starting from the positive x-axis here. So that's a negative rotation, negative half rotation this way, and then out to 2 pi. Okay, and so again, starting on that positive x-axis, and 2 pi is a full rotation. So this is the domain that we're looking for here. Now we're going to come back to that in just a second. Now let's take a look at the equation. Now, experience would tell me here that a lot of times when people look at an equation like this, they get thrown off by the presence of the trigonometry in there. Okay, well, let's deal with that. There's a little trick that mathematicians use to kind of get around issues like that when they're solving an equation. What we're going to do here is look at it this way. You don't know what theta is. Okay, theta is the unknown. You're going to try to figure out what theta is. Well, if you don't know what theta is, then you don't know what sine of theta is. So let's just call it x right now. Okay, so over here, we might make a little note here. We're going to let x be equal to the sine of theta. And we'll come back to that in a little bit here. There are two levels to these problems. Okay, there's the algebra and then there's the trigonometry. Well, let's deal with the algebra first. The trigonometry in these questions here is going to be the last thing that we're going to deal with. So we're going to get the x by itself on one side of the equation. Let's bring the 3x over. We'll bring the 6 over. Now we'll divide by that 2 and we'll get that x is equal to negative 1/2. Good. So that is us solving the algebra portion of this problem. Now let's move in and deal with the trigonometry because we know that sine of x, we know that x is the sine of theta. And so now we get it down to this equation right here. Now this is something that we're fairly familiar with. Okay, sine of theta is negative. Okay, sine is negative in quadrants 3 and 4. I write that down here. So now I can see that I'm going to actually get 4 different solutions here, okay? The points of intersection where that terminal arm intersects with my domain, okay, the lines of my domain, those each indicate possible solutions here. Now, that's the first part of this. The next thing we're going to do here is we're going to use or find the reference angle by doing the inverse sine of the absolute value of that ratio. Remember, I don't want to worry about the negative there. And when I do that, and if you just think back to your unit circle, you should recall that this is going to be pi over 6. Now, I know that I'm in radians because when I look at my domain, I'm seeing pi and 2 pi there. Okay, that's a good indication that we're in radians here. So now, there's my reference angle. That is the angle within the right angle triangle that I'm going to use to figure out what the angles are, the answers are, okay, or the rotation angles in quadrants 3 and 4. Now, so what I'm going to do here is I'm going to identify a third quadrant angle, or my third quadrant angles, I should say, and my fourth quadrant angle. Sorry, you can't see that. So, first of all, let's start on the negative rotation. When I go from here to here, okay, that's my pi over 6. Remember that my reference angle is the angle between the x-axis and the terminal arm. So that's pi over 6. I'm going clockwise, so it's going to be negative. So negative pi over 6. There's my first answer. Now I come all the way across to here. Here's my next solution. This angle here is pi over 6. Okay? So this is going to be 5 pi over 6. Okay? Because remember what's going on here. When we talk about pi over 6 here, what we're doing here is dividing the circle, or the half of the circle, into sixths. Okay, there are 6 in the denominator, 6 below the x-axis, 6 above the x-axis here. So when I want to go to this point right here, where this is my reference angle, that's going to be 1, 2, 3, 4, 5 pi over 6. And that's going to be in the third quadrant, 5 pi over 6. You can do that algebraically if you wish, but I think it's far easier to just see it, okay, to get a a picture of what's going on here. Now let's jump to the positive rotation. And we come all the way around here. So right here, just as we saw, just as we saw down here, there are 6 pi over 6's here, 6 of them here. And I want to go one more to get down into the third quadrant. So that's going to be 7 pi over 6. And then to get to this one here, I'm going to go around almost all the way around the full circle. Okay, there are 6 of them here. There's going to have another 5 here because all I want is this one little reference angle left over there. So that's going to be 11 pi over 6's. Okay, and there we go. Those are the 4 solutions that we were looking for. 5 pi over 6, 7 pi over 6, negative pi over 6, and 11 pi over 6. But that's not the end of this problem here, because the question is asking us to also come up with a general solution. So this is the specific solution for that domain. When we talk about a general solution, what we're referring to is really, if you were to let this thing go forever and just keep rotating around, if you were to open up the domain to all real numbers, what is the pattern that is going to be established here? So one way of writing this, or one way of doing this, is to come up to our diagram here. Here's a terminal arm, here's a terminal arm. Typically when we write coterminal angles, because that's really what we're identifying here, the coterminal angles, what we're going to do here is we're going to come up with an angle representative for each one of these terminal arms, and usually we use the principal angle or the positive ones. So just go back up to our specific solutions here. Let's grab the smallest positive ones that deal with both of those terminal arms. So for example, this one right here I know is going to be 7 pi over 6. Okay. This one over here is going to be 11 pi over 6. Actually, I can see right now I made a little mistake here. This is supposed to be negative. Sorry, I forgot to throw the negative down there. So my two answers here for my general solution will be 7 pi over 6, comma 11 pi over 6. And to each of these we would add n times 2 pi, okay? 2 pi representing a full rotation around the circle. We're going to add n of them, where n is an element of the integers. So as long as n is an integer number, not a fraction, but an integer number, then we're going to add complete rotations or subtract complete rotations, and those are all of the solutions to that particular equation.
Solve cotangent squared of x is equal to the negative cotangent of x, where x is between negative pi and pi.
So this question right here is more in line with a lot of what a lot of the other questions are going to look like. They're going to be quadratics. We're seeing the square here. Okay, but just like before, the first thing we want to do here is take a look at our domain that we're working with, and let's identify where it is that we're looking here. So negative pi, okay, so it's going to be from the positive x-axis, that is a negative half rotation, out to positive pi, so a positive half rotation. So somewhere in there, okay, is going to be our solution. So here's our negative pi up here, our positive pi. Now let's take a quick look at the equation here. Cotangent squared of x is equal to the negative cotangent of x. Now, and again, we might look at that and say, you know what, I don't want to work with the trigonometry right now, let's not. So let's let cotangent of x, oh, I don't know, let's give it another variable here. Let's call it a. So this becomes a squared, and that's going to equal negative a. Now, it's very tempting at this point to want to just divide both sides by an a, by a variable here, but you should never do that. Because what you end up doing here is losing possible solutions, okay, by canceling that out, okay? And just to show you here, because one of the obvious answers to a here that makes the left side and the right side equal would be 0, okay? And if you divide both sides by a, okay, you are in essence losing that, and you really can't do that. You can't divide by that 0. And I know that's kind of a weird bit of a stretch there, but don't divide out the variable. Bring the variable over, particularly if it's a quadratic. Bring that variable over to one side, or you could bring the a squared over to the other side if you wanted, and then factor. That really should be how you approach these quadratics. And now I've got one of two scenarios here. Either a is equal to 0, and we had mentioned that already, or a plus 1 is equal to 0, meaning that a would have to be negative 1. So either a is equal to 0 and you multiply that out, the whole thing is equal to 0, or is a is equal to negative 1 and the whole thing goes to negative 1. Or sorry, the whole thing goes to 0 because this would go to 0. Now let's put our a away and put the cotangent of x back in. So the cotangent of x is either equal to 0 or negative 1. Now, when you're talking about cotangent, it's important to remember that over here, we'll just put it over here, that when you're dealing with the cotangent of theta here, it's going to be the x-coordinate of the point on the terminal arm divided by the y-coordinate. And so when I say that the cotangent of some angle here is equal to 0, okay, what I'm saying here is that this ratio is equal to 0, and the only way that that could ever happen is if the x here is equal to 0, not the y. Dividing by 0 is undefined, so y can't be 0 in this case. It's got to be the x. And so what I'm trying to do here is I'm trying to find where are the angles here where the x-coordinate is equal to 0. Well, let's take a look here. As you go around the circle, just think about it. Think about all the points along a circle here as you rotate around. Where does x become 0? Where is the x-coordinate 0? Well, that's going to happen on the y-axis. So it's either going to happen there or there. Okay? Which means, particularly if we come around this negative rotation first, okay, our first angle here is going to be negative pi over 2. And again, we know we're in radians because the domain that we're given here is given to us in radians. So negative pi over 2 is going to be this angle right here. Likewise, when we jump up to the positive rotation, I only have to go up to the y-axis, and so I'm going to get my other angle here would be positive pi over 2. Now notice I'm not identifying quadrants that this is in because really these are quadrantal angles. They're between quadrants. I'm also not identifying the reference angle because if you look it up here, and I know there's some disagreement about this, but if you look it up, you'll often see that the reference angle is defined as the acute angle between the terminal arm and the x-axis, and 90 degrees just isn't acute. So I'm not finding the reference angle. Okay, I'm just using what I know about the ratios for the ratio for cotangent to figure out what that angle is. Here though, this is a different story altogether because the cotangent of x is now equal to negative 1. This isn't going to have any kind of weird quadrantal property here. So what I'll do here is I will find the reference angle here, and this is going to be the inverse cotangent of the absolute value of negative 1. And again, an absolute value because I don't want to use the negative there. The negative simply tells me what quadrants we're in. Oh, and we should probably identify that. Where is cotangent going to be negative? Well, okay, cotangent is going to be negative in quadrants 2 and 4. And the reference angle here will be pi over 4. Meaning, therefore, that x, if I take the negative rotation, okay, the negative rotation here, that'll be negative pi over 4. Okay, and then I would move along my positive rotation here. Now, again, remember when I say that the reference angle is pi over 4, what that means is I'm taking pi, top half of the circle, yoink, and dividing it into quarters. And if I'm in the second quadrant here, that's got to be this terminal arm, which means 1, 2, 3, 3 pi over 4. Okay, good. Those are the specific angles that we're looking for here. Negative pi over 2, negative pi over 4, 3 pi over 4. Now we're going to talk about the general solution here. Now, at this point here are my terminal arms. They're there and there. There are a couple of ways you can write this. Now I know some of you are going to be happiest just doing it like this. Just let's list them off here. So this is going to be, you might go negative pi over 2, pi over 2, negative pi over 4, 3 pi over 4, all of these angles, and then we would add n times 2 pi where n is an element of the integers. Okay, and that's fine. That does the job here. It is, however, a little redundant. Okay, and the reason it's redundant here is because particularly when you're dealing with tangent or cotangent, you're always going to get this scenario here where you've got a terminal arm here and then straight across on the other side of the origin another terminal arm. Terminal arm here, and then across is going to be this other terminal arm here. So I don't need to list all of them. I really only need to list 2 of them and then just adjust my period. So for example, I might take the positive rotation here, because normally I want to be using the principal angle or the positive angle. And so my angles here would be pi over 2, 3 pi over 4. So I might write pi over 2 and 3 pi over 4. But this time I would add n pi, where n is an element of the integers. I would only add, seems to be a little bit of a rut in the table there. Hold on. Anyway, I would only add pi a half period to that. If you add the half period, you go from here down to here. Add it again up to there. Same thing with this terminal arm. Add a half period, you're down to here. Okay. Or I should say a half rotation, not a half period, because the period for cotangent is in fact just pi.
Solve 4 secant squared of theta minus 16 is equal to 0, where theta is between 0 degrees and 360 degrees.
All right, now that you've seen just a couple of straightforward basic examples, we're going to look at one now, or we're going to look at a handful here that have got something a little bit unique about them, things that you want to look out for. But first of all, before we jump into this problem, notice that our domain here is 0 to 360. So we are talking about, okay, we're in degrees, I should say, which is important. I think for some of you that'll be like, okay, finally back to degrees. Okay. And what does it mean to go from 0 to 360? Well, 0 is the positive x-axis, and 360 refers to a full positive rotation. So there's where our solutions are going to be, somewhere in there. Now, move over to the problem here. And again, we've got this secant squared of theta in there, and I suspect that we could probably make that a little bit nicer here by simply saying that secant of theta, just for the time being, we're going to call that x. So 4 times the secant squared of theta minus 16 is going to be really 4x squared minus 16 is equal to 0. Now, a couple of things that you can do here. Well, there's one thing you should do, then there's a couple of things you can do to approach this. The first thing I would do here is simplify this by simply dividing everything through here by 4. Okay? As long as you divide everything by 4, you're okay. The equation stays an equation, okay? You haven't changed anything, you haven't altered the value of one side or the other. And everything here is divisible by 4. Now, at this point right here, there's a couple of ways you can interpret this. Some of you are going to see this as a difference of squares. You would say that this is x minus 2, x plus 2 equals 0. And that's wonderful. Some of you are going to look at this and say, well, wait a minute, I could just do this. I could just say x squared is equal to 4. Oops. And that is true. Now, however, if you're going to do this, I just want to remind you here of something small, and this is going to bite a lot of people on the butt, and I know that it does because I've watched it happen a lot of times here. The square root of 4 is 2. But when you're solving the equation like this, you need to put in plus or minus, because squaring, okay, remember, squaring gets rid of the negative if it exists here. So when I'm squaring a number to get 4, I don't know whether it was originally it was the positive or the negative value here. Now, if you use the difference of squares, okay, the positive and the negative are going to fall into your lap automatically. If you don't, just please pay attention to the fact that you're taking a square root and you need to include the plus or the minus there. Now let's put back in our secant. So the secant of theta is going to equal positive or negative 2. Now, I don't really want to be working with secant, okay? And I know that secant is 1 over cos. Okay, so let's think of it like this. This is 1 over cosine of theta. And so what I'll do is I'll reciprocate both sides to get the cosine of theta is equal to plus or minus 1/2. Okay, reciprocating the plus or minus doesn't change anything, so I just leave it out front there. Okay, good. Now, what does the plus or the minus mean? Well, for me, what that means is I'm going to have 2 answers where cosine is positive, 2 answers here where cosine is negative. Basically, that plus or minus is going to communicate to me all 4 quadrants. And remember, we're still just talking about a single positive rotation here, so we're just going to walk all the way through all of these here. Now the next thing I want to do is figure out what my reference angle is. And this will be the inverse cosine of positive or negative 1/2. Okay, and in degrees, that's going to be 60 degrees. So, normally what I would do is I would identify the different quadrants and the angles in the different quadrants. However, in this particular case here, I'm going to get one angle in each of the 4 quadrants. So theta here, I'm just going to walk it through. Theta is going to be 60 degrees. Okay, when I move over here into the second quadrant, remember this is my reference angle, this is 60, so this is going to be 120. Down here it's going to be 180 plus 60, so 240. And then all the way around over here it'll be 360 less my reference angle, less 60, so 300 degrees. Okay, good. Those are the four solutions, the four specific solutions in the domain that I've been given. Now I want to identify the general solution. And with the general solution, what I could do is I could list off all four of those angles and then just say plus n times 360 degrees, where n is an element of the integers. Because you can start at any one of those angles and you just continue to add a rotation or subtract a rotation, complete rotations, not fractions, but complete rotations, and you'll get answers to that equation. But you can be a little bit sneaky with this one too, because of the way the answers are written here, because of the way they show up here. I've got this terminal arm in the second quadrant and also one in the fourth, and those are going to differ by 180. These two here are also going to differ by 180. So I can kind of condense this a little bit, and I can maybe just pick my 60 degrees from my first quadrant, pick the 120 degrees from the second quadrant, and then what I'll do here is I will add not n times 360, but n times 180, where n is an element in the integers, just to make that a little bit cleaner there, okay, a little bit less bulky. So here's another way of writing that general solution.
Solve 2 sine squared of x plus 5 sine of x minus 3 equals 0, where x is between 0 degrees and 360 degrees.
Okay, this question right here, I actually really like this question, and I'll show you why in a second here. So just like we did with the previous ones, first thing we want to do is take a look at the domain that we're given, okay, over which the answers are going to be found. And this is, again, we're in degrees, and this is just a basic one complete positive rotation. Okay, good. Now, let's take a look at this. This equation is in terms of sine. So maybe what we'll do here is, and it's the sine of x here, so maybe we'll let sine of x, we'll write that with a here, rewrite that. So this becomes 2a squared plus 5a minus 3 is equal to 0. And this is a quadratic. So to solve that quadratic, we want to factor it. But don't spend a lot of time factoring. If it doesn't factor really quickly for you, then I would just jump to the quadratic formula and use that, okay? I don't spend a lot of time fighting with this if factoring is something you're a bit weak in. But I would find that for most questions that you're going to get at this level here, because factoring is not what we're trying to teach here, factoring is a tool that we're using, you should find that most of these things actually factor down pretty easily if you were just to do guessing and checking. So for example, 2 can be broken down into 2a and 1a. Okay, 2a times a is going to be 2a squared. Now, the product of these two values right here has to be negative 3. And when I distribute everything through and I add the two linear terms, I should be getting a coefficient of 5. Now, that suggests to me that this has got to be 2 times 3. So I'm thinking this has got to be 3 here. And so that'll give me 6. And then I'll subtract 1a from that to get 5. And then negative 1 times 3 is negative 3. And so taking those individually, in order for the product to be equal to 0, a has either got to be equal to 1/2 or a is equal to negative 3. So now we've dealt with the algebra portion of this problem, and I hope that's relatively quick. It is kind of an assumed skill at this point. Now let's plug in the sine of x. So sine of x is either equal to 1/2 or the sine of x is equal to negative 3. So we've got two different equations here that we've got to solve, and this is pretty standard for this type of problem. Okay, so let's take a look at this one here. Sine of x is positive, so it's going to be in quadrants 1 and 2 here. We want to figure out what the reference angle is, and that'll be the inverse sine of the absolute value of 1/2. And if you think a little bit about that, you should kind of zero in really quickly here. That's got to be 30 degrees. And so what we get here is this has got to be 30 degrees because I'm jumping right to my terminal arm. So my first angle here in quadrant 1 is going to be 30 degrees. And then I'll just list this off here. The second angle I'm going to get to is going to be over here in quadrant 2, where this is 30 degrees, so that's going to be 150. So my two answers there are going to be 30 and 150. Quadrant 1, quadrant 2. Now I come over here. Sine of x is equal to negative 3. So sine is negative in quadrants 3 and 4 here. But here's where we run into a little bit of difficulty. If I try to find the reference angle here, I'm going to get an error. And the reason for that is because sine and cosine, remember how they're defined here. Sine of an angle is going to be the y-coordinate over the hypotenuse, the radius here. The cosine of an angle is going to be x over r, okay? In the triangle here that we're given, when we build these ratios here, the r is taking the place of the hypotenuse. And in the right angle triangle, the hypotenuse is always the largest side. Now, that means that these ratios will always be less than or equal to 1. Okay? These guys here, the sine and cosine ratios are always between, when you account for the full circle here, -1 and 1. Okay? So sine has got to be somewhere between -1 and 1. So when we get an equation right here where it's all of a sudden set equal to -3, okay, which is outside of this little interval here, we get an error. There's no solution coming from this particular equation here. So it kind of shuts it down here. This is the reason why I like this problem, okay? Because it's testing your knowledge of the trig functions and of another property here that we haven't really explored in a lot of detail up to this point. So a question like this, this will be one of those things here where I'll often see students that'll do this. They'll get to this point here, get an error, assume they've done it wrong, and then they'll go back and try to fix it by changing something here. Even though it's correct, this is just a dead end, okay? So don't be thrown off by the fact that you get an error here, that there's no solution. That happens periodically. So the only two solutions that we're getting here are 30 and 150. And so now if we want the general solution, we would simply say that the answers here would be 30 or 150 plus n times 360 degrees, where n is an element of the integers.
Solve 3 cotangent theta sine theta plus 1 is equal to cosine of theta, where theta is between -pi and 2 pi.
Okay, now here's another problem, another take on the solving of the equation here, another way of asking the question here. Before we look at the equation, let's look at the domain here. So we're back to radians, and we've got a -half rotation. We go from 0 down there to -pi, and then we're going to do a positive full rotation out to 2 pi. Okay, so our answer should show up somewhere in there. Now we come and take a look at this, and oh boy, look at this. It's got cotangent of theta, sine of theta, cosine of theta. Now, if you've got an equation that has got multiple trig functions in it, you got some work ahead of you here, because you really can't work with that. Unless you can factor them apart or use an identity to replace something, okay, that's kind of a dead end here. Now, in this particular case, though, okay, you can't factor these things apart. However, you do have the option of using an identity. And I hope you see this right away here. So in this particular case here, replacing these things with variables like we would do before to solve kind of the algebra of the problem, that won't work here because these are all different. You'd have to make this like 3xy plus 1 equals z, and there's nothing you can do there. However, cotangent of theta can be replaced with the cosine of theta divided by the sine of theta multiplied by the sine of theta plus 1 is equal to the cosine of theta. Okay? Now, sine of theta will cancel with sine of theta. Now that is true. That is true, but we're going to come over here. We got to make sure that we identify this. I can make that cancellation here so long as the sine of theta does not equal 0. Okay? And now let's just kind of solve this little problem right here just to make sure that we're not getting answers that aren't correct here. Where does the sine of theta go to 0? Well, sine of theta is defined as y over r. Okay, so the y coordinate of a point on the terminal arm over the radius. The only way that's going to equal 0 is if the y coordinate is 0, and the y coordinate is 0 on the x-axis. Okay, on the x-axis here. So we're talking about angles like 0 degrees. Well, are we in degrees? No, we're in radians. So 0, pi, 2 pi. So this is going to show up here. Basically, theta cannot equal multiples of pi. Okay, it can't equal any multiple of pi or else we're going to run into some problems there. Now, let's come back here. So as long as we avoid that, we should be okay here. So this becomes 3 cosine of theta plus 1 is equal to the cosine of theta. Now, you may want to replace these cosines with x, or you may simply want to bring that cosine over, subtract it, just treat it like an algebraic object here. Make this 2 cosine of theta plus 1 equals 0, and then solve for the cosine of theta, and you'll get that cosine is going to equal negative 1/2. Okay, so what does this tell us? Well, cosine is negative in quadrants 2 and 3. So now we got to figure out what the reference angle is. That'll be the inverse cosine of the absolute value of negative 1/2. And that is going to occur, just think about it here, think about your unit circle, your special triangles, that'll occur at pi over 3. Okay, so bearing in mind that that was our domain here, we've got, looks like 3 different answers here that we're going to be looking for here. So first of all, let's start on that that negative rotation, I should say, the negative rotation. I'm dividing pi into thirds, and I'm coming over to here. Well, there would be a third here, a third. So what I've got here in the third quadrant, okay, is going to be negative 2 pi over 3. Okay, negative 2 pi over 3. There's the first answer in the third quadrant there. Now I'm going to come around and look at the positive rotation. I've still got a second quadrant angle that I got to find here. Let's go around here. So if I rotate out to here, I'm going to rotate through a third of pi, another third, so that's going to be positive 2/3 of pi. And then I'm going to come back down here and back into the third quadrant. And so this is going to be 3 pi over 3. That's pi. That's the top half of the circle is 3/3 of pi. And I got one more third to get into the third quadrant there. So this is going to be positive 4 pi over 3. Okay, so just think of it like this. I'm cutting the circle up, the half circle up into thirds. So to get down to here is going to be 1, 2, 3, 4 pi over 3. Now we still haven't gotten the general solution yet. So we'll put that over here. My general solution, I've got 2 terminal arms here. I really only need representatives for each of those, and I'll use the positive ones, so the 2 pi over 3 and the 4 pi over 3. So 2 pi over 3, 4 pi over 3, and to that I'm going to add 2 pi, where n is an element of the integers. Those are the coterminal angles, and those will give me all of the solutions to this problem over the entire infinite domain.
Solve cosine of x minus 50 degrees is equal to 0.75, where x is between 0 degrees and 360 degrees.
Here's another good question, and something you should be looking out for here. Notice in this case here, it's the cosine of x minus 50 degrees. In this case here, the algebra happens after the trigonometry, because the algebra little bit here is within the trig function here. So that's what makes this kind of a problem unique. Now we're going to come back to this again in just a second here, but first let's take a quick look at the domain. And if we look at our coordinate plane here, we're in degrees, 0 to 360. Again, here's just a nice once around the circle there. Now let's take a quick look at this. Notice what this is doing here, and think about this in terms of work that we've done previously in this course. X minus 50 degrees, okay, x minus 50 in there, is going to be a horizontal translation 50 degrees to the right. So what this is going to do is this is going to move all of our answers to the right. Now we're going to get to that in just a little bit here. Now, just like we did before where we replaced the trig function with a variable, what I'm going to do here is I'm going to replace the algebra here with a variable. So I'm going to let theta equal x minus 50 degrees. I'm going to come back to that in a second, okay? Because it's a part of the problem that's kind of throwing me off right now. So this is going to be the cosine of theta is equal to 0.75. Okay, now cosine of theta is positive, and I know that cosine is going to be positive in quadrants 1 and 4. Then I'm going to find the reference angle by doing the inverse cosine of the absolute value of 0.75. Now, don't let this throw you off here. Don't look at that and go 0.75. Well, that's 3/4. And don't get confused thinking, well, that's not on the unit circle. I know it's not on the unit circle. I've watched all sorts of students get thrown off by questions like this because they forget that they can just go to the calculator and enter that in. And when you do, you get an answer that's basically 41 degrees. That's approximately 41 degrees, but that's what we're going to use. Okay? You typically round angles to the nearest degree when you're doing something like this. With radians, you know, it could be the nearest tenth or the nearest hundredth, but normally with degrees, you go to the nearest degree. So now what we're going to do is we're going to put these things in quadrant 1 and quadrant 4. Okay, so we got a first quadrant angle, and then we're going to get a fourth quadrant angle here. In quadrant 1, we just rotate up from the positive x-axis to the terminal arm, and that's going to be 41 degrees. Now, we're going to come all the way around over here, and that's going to be 360 degrees, but we're going to get less 41, and that'll end up being 319 degrees. Great. But we're not quite done with that, okay, because actually the answers here, they weren't theta. The angle here wasn't theta, it was x. So now what we're going to do is we're going to replace these and make this x minus 50 degrees is going to equal 41. Okay, and I'll give myself a little bit of space. X minus 50 degrees is going to equal 319 degrees. Okay, now bring that 50 degrees over. When you add 50, we're going to get that x could be equal to 91 degrees. Now see, and here's an interesting one. And this is why I don't, for example, I didn't immediately say, this is going to be x in quadrant 1, because 91 degrees isn't in quadrant 1, it's in quadrant 2. Just like over here, when you bring that 50 over, you're going to get x is equal to 369 degrees. But now think about that. 369 degrees, that's not in quadrant 4 anymore. That's now rotated through. This has now been rotated into quadrant 1. And so this is actually going to be x is equal to, now think about that, that's 9 degrees over. So the answers that we're looking for, okay, the answers are going to be 9 degrees and 91 degrees. Now, in general, the solutions will be, and this is actually easy to do at this point, this is going to be 9 degrees, comma 91 degrees, plus n times 360 degrees, where n is an element of the integers. Okay? So really interesting math going on here particularly when we jump from one full rotation to the next, and then having to kind of dial that back and deal with it in terms of the principal angle. Good question.
Solve 2 sine of x plus x minus 5 equals 0 in radians.
Okay, we're going to finish off this little lesson here with just an example of something, or an example of an equation that does something a little different. Now notice that when I look at my domain here, I've simply said in radians. So basically I'm implying this is all real values, okay, all reals, just with the understanding that the mode that I'm in is in radians here. So I am looking for a general solution overall. But what makes this particular question unique is that I've got the sine of x plus x. Notice that the independent variable shows up within a trig function and then on its own as a term. Turns out we really don't have at this point, okay, a nice algebraic way of dealing with that. This is a calculator question. Okay, the expectation is that you're going to jump right to the calculator to do this. So let's do that. Okay, so I've already entered that in. So we've got 2 sine of x plus x minus 5 in y1. Now you have to remember you're in radian mode. Okay, you got to be in radian mode. And then 2 sine of x plus x minus 5. Now I do a lot on my calculator here, so I'm not quite sure what the window settings are, so I'm just going to press zoom and then number 6 to go back to my standard zoom settings and just see what I get. If this doesn't give me kind of a clear answer, I will adjust my window settings. Okay, now look at that. Look at what we've got here. It's this nice little, okay, this nice little S-shaped curve here that continues to rise to the right here. And it looks to me like it's only got one solution. That is the only answer. So I'm going to find that x-intercept there using the 0 function on the calculator. And I will move closer. I have to make sure that that x-intercept is between these two lines. So I go to the left of it, press enter, it draws that little line there, it draws that triangle up top. I move to the right, press enter, it draws a little triangle there, it draws the line. As long as the x-intercept is between those two lines, the calculator will find it when I press enter again. And there it is. And so my answer here is going to be roughly 5 point, did I say what to round it to? Well, we'll round it to the nearest hundredth here. What is that? 5.85. Okay. X is equal to 5.85, approximately. Okay, and that actually turns out to be the general solution as well, because there was only one answer to this problem.